Okay, today's lesson is going to be on section 5.2, and we're going to talk about values of trig functions and then introduce some very basic fundamental trig identities as we go through the lesson. So we're going to spend the next few days talking about right triangles and trig functions that are associated with right triangles. So if you look at our triangle here, we've got an angle here in the bottom part of this triangle we call theta, and then we've got these sides in this right triangle. So this A right here is adjacent to where theta is. Okay, this is not always the adjacent side, but because theta is right here, the side that is next to or adjacent to theta is this side on the bottom of the triangle called A. And then opposite of angle theta, or across from angle theta, is... Sorry about that, had a little interruption with the announcements, but as I was saying, opposite of angle theta, which is right here, is this side B. And once again, this is not always the opposite side. Sometimes the opposite side is down here if the angle theta is up here in the top. Okay, so you have to pay attention to where the angle is, because that'll tell you what your adjacent and your opposite sides are. And then the hypotenuse is always across from the right angle in the right triangle, and in this case I've called the hypotenuse C. So we're going to recall from geometry this acronym Sohcahtoa. And so what this helps us do is know what the first three trig functions are in a right triangle. So for sine of theta, that is O over H, or the opposite over the hypotenuse, which in this triangle, if this is our theta, the opposite side is going to be B, and the hypotenuse is going to be C. So this would be B over C in the triangle that we're talking about. For cosine theta, that is the adjacent over the hypotenuse. So adjacent divided by hypotenuse, which in our triangle, if we take a look here, here's our angle theta. The adjacent side that's next to that angle is A, and the hypotenuse is C. So this would be A divided by C. And then for tangent theta is going to be opposite over adjacent, which in our triangle is going to be B divided by A. Now, if you know those three trig functions, then the other three are really easy because they are just the reciprocal functions, which means that we're just going to flip our fractions. So sine theta and cosecant theta, that's what the CSC stands for, is cosecant theta. That's going to be the reciprocal of sine theta. So instead of being O over H, it's going to be H divided by O, the hypotenuse over the opposite. And in our triangle, that's going to be C divided by B. Cosine and secant are reciprocals of each other. And so if cosine is A over H, that means that secant is going to be H over A. And in our triangle, that means that it will be C divided by A. And then tangent and cotangent are reciprocals of each other. So if tangent is O over A, then that means cotangent is going to be A over O, or in this case of our triangle, A divided by B. So remember, you have your original three trig functions that you learned about in geometry. That would be sine, cosine, and tangent. And then we're adding in three more, which are the reciprocals, cosecant, secant, and cotangent. Okay, in example 1, we're going to use the definitions that we just talked about to decide whether the following equation is true or false. So I want to say, is tangent theta equal to sine theta divided by cosine theta? And so what I'm going to do here is I'm going to draw a picture of a right triangle. I'm going to put an angle theta down here in the bottom of my triangle, and then I'm going to label these sides A, B, and C. Okay, well, if I figure out what sine theta is going to be, sine theta is going to be the opposite over the hypotenuse, and so that is going to be B divided by C in this particular triangle. Cosine theta is going to equal the adjacent over the hypotenuse, so that would be A over C, and tangent theta is going to equal to the opposite over the adjacent, which would be B divided by A. So in this equation here, I know that tangent theta is B divided by A, and I want to know, is that equal to sine theta divided by cosine theta? Well, sine theta is going to be B divided by C, and cosine is going to be A divided by C. And then what I remember about dividing fractions is that dividing by a fraction is the same thing as multiplying by the reciprocal of the denominator. So I'm going to instead make this a multiplication problem and take the reciprocal of this denominator, a over c, which becomes c over a. Now when I do that, what happens is that these c's cross-reduce out, and so this becomes b over a, and so what I recognize is that this left-hand side was also b over a, and so that means that this equation that we started with is a true equation. Okay, we're now going to go into finding the value of each of the 6 trigonometric functions that we've talked about of an angle theta given in a triangle. So if you see here, we have our triangle. Theta is right here. We are given that this side is 3 and that the hypotenuse is 5, and we are not given this side of the triangle. So the first order of business is to find what that side is, and so I'm just going to call that side A. I could call it really anything that I wanted to, but I'm going to call it side A. And step 1 of this process is to use the Pythagorean Theorem in order to find that side A. Okay, so I remember from geometry that the Pythagorean Theorem says that the leg squared plus the other leg squared, which in this case is 3, is going to equal to the hypotenuse squared, which in this case is 5. And so just calculating this, I'm going to get a squared plus 9 is equal to 5 squared, which is 25. And I'm going to subtract 9 to the other side, which is going to give me 16. And that tells me that a is equal to 4. So I can now say confidently that that side opposite of the angle theta is going to equal to 4. Okay, I'm now ready to write down my answers. So sine theta is going to equal to the opposite side. Well, if this is angle theta, then the opposite side is 4, divided by the hypotenuse, which is 5. So sine theta is going to be 4 divided by 5. That tells me that cosecant theta is equal to the reciprocal of sine theta, which in this case would be 5 divided by 4. So once I find sine theta, it's pretty easy to find cosecant theta because all I have to do is take the reciprocal. For cosine theta, I remember that that is the adjacent side over the hypotenuse. So the adjacent side of this angle theta is going to be the 3, and the hypotenuse is going to be 5. So cosine theta is going to be 3/5. Well, now that I know that, I can pretty easily tell you what secant theta is going to be, because that's just going to be the reciprocal of cosine, which in this case will be 5/3. And then finally, tangent theta is going to be the opposite over the adjacent. And the opposite side in this triangle is the 4, and the adjacent side is the 3. So this will be 4/3. And if tangent theta is 4/3, then I know that cotangent theta is just the reciprocal of that, which will end up being 3/4. So as you can see, if you can figure out what sine, cosine, and tangent are, finding the reciprocal functions should be pretty straightforward. Okay, on the next problem, a couple of things are different, although this problem is pretty similar to example 2. First thing I notice is that the angle theta is in the top this time. And so what that means, I'm going to use a different color here, it means that this is actually the opposite side, since it's across from the angle theta, and 7 is the adjacent side. Of course, this is always the hypotenuse. Okay, so in this particular case, we do not have the hypotenuse, so once again, we're going to use Pythagorean Theorem to find it. So if we set this up, leg squared plus leg squared is going to equal to the hypotenuse squared. And calculating 4 squared plus 7 squared is going to be 65, which is equal to c squared. And so that means when I take the square root, I'll get c is equal to the square root of 65. And so this is going to be square root of 65 for my hypotenuse. Now, when I do sine of theta, that's going to be the opposite side over the hypotenuse. And since I labeled this here, I see that this is the opposite side, since this is where theta is located. And so that's going to be 4 divided by the square root of 65. Now, that's not going to be an acceptable answer because we don't want to have square roots in the bottom. And so I'm going to rationalize this by multiplying by root 65 over root 65, which is going to give me 4 square roots of 65 over 65. And that's going to be the answer that I want to type in into the online homework system. Now, once I have sine theta, it's pretty easy to get cosecant theta, since I just need to take the reciprocal. And what I'm going to do when I do that is I'm just going to take the reciprocal of what I originally wrote down. That way I don't have to re-rationalize the problem. So this is just going to be square root of 65 divided by 4 for cosecant theta. Okay, for cosine theta is going to be the adjacent side, which is 7, divided by the hypotenuse, square root of 65. So this is going to equal to 7 divided by the square root of 65, which again, I'm going to rationalize the same way that I did before. So 7 square roots of 65 over 65. For secant theta, since that's the reciprocal of cosine, we're just going to take the reciprocal of 7 over square root of 65. And so that's going to give me the square root of 65 divided by 7. And that would be what I typed in. And then finally, for tangent theta, that's just going to be the opposite over the adjacent. And so the opposite side is going to be 4. The adjacent side is going to be 7. So that will just be 4 divided by 7. And for cotangent theta, we're just going to do the reciprocal, and the reciprocal of 4/7 would be 7 over 4. Okay, so before we go any further, we're going to write down the first 5 fundamental identities that we've already sort of looked at. And so the first 3 are called the reciprocal identities. Cosecant theta is equal to the reciprocal of sine theta, so that would just be 1 over sine theta. Secant theta is going to be the reciprocal of cosine, so this would just be 1 over cosine theta. And cotangent theta is going to be the reciprocal of tangent theta, which is 1 over tangent theta. The next 2 identities are called the quotient identities. The first one is tangent theta, and we proved earlier in example 1 that tangent theta is equal to sine theta over cosine theta. And then the other quotient identity just uses the fact that cotangent is the reciprocal of tangent. So if I have that tangent is sine over cosine, that means cotangent is going to be cosine theta divided by sine theta. Okay, so now that we have those identities, hopefully you wrote them down for your notes so that you're able to look at them. We're going to use those to find the exact value of each of the 4 remaining trig functions of the acute angle theta given 2 of the trig functions. So sine theta is 6 over 7, sorry. That means that the reciprocal function cosecant theta is going to equal to the reciprocal of 6 over 7, which will be 7 over 6. So that one was pretty easy. And then cosine theta is root 13 over 7. So that means that secant theta is going to be 7 over the square root of 13. But we want that to be rationalized, which means we're going to write 7 square roots of 13 over 13. And then for tangent theta, in order to find that, we can use the fact that tangent theta is sine theta over cosine theta. And so this is going to equal to 6 over 7 divided by square root of 13 over 7, which is the same thing as 6 over 7 multiplied by the reciprocal of the denominator, which is going to be 7 over the square root of 13. What I notice now is that the 7s will cancel, and so this will give me 6 over the square root of 13. But that's not going to be an acceptable final answer. It's going to have to be rationalized. So I'm going to rationalize it by multiplying by root 13 over root 13, and that's going to give me 6 square roots of 13 over 13. And then cotangent theta will be found just by taking the reciprocal of tangent theta, and I'm going to take the reciprocal of this version of tangent theta, and so that's going to give me the square root of 13 divided by 6. Okay, on example 5, we're only given one of the 6 trig functions, and we're asked to find the other 5. And so what we're going to do here to make this much easier is we're going to draw a picture of a triangle that has a theta where the sine of theta is the square root of 2 over 6, which is given in our problem. So here's my right triangle. I'm going to put my theta down here, which I don't have to put it down there, but I could put it down there if I wanted to. The other option would be to put it in the top of the triangle, but it's really up to you. And then if sine theta is root 2 over 6, I know that sine theta is the opposite over the hypotenuse. So I'm going to put on this triangle that the opposite side is square root of 2 and the hypotenuse is 6. So this is kind of step one, is to draw a picture so that you can see what is going on. Now we're missing a side of this right triangle, call it A. In order to find A, we're going to use Pythagorean Theorem. So I'm going to kind of abbreviate that, use Pythagorean Theorem, and if I use the Pythagorean Theorem, that's going to say that A squared plus the square root of 2 squared is going to equal to 6 squared. And so that's going to be A squared plus 2, since square root of 2 squared is 2, is equal to 36. And so that means that A squared is going to equal to 34, so that A is equal to the square root of 34. Okay, so now that I know that this bottom side of the triangle is square root of 34, I should be able to go about doing everything like normal. So for this angle theta, remember that we put our angle theta right here. We already know sine theta, that was given to us. And so now we can say what cosecant theta is. Since it's just the reciprocal, that's going to be 6 over the square root of 2, which when we rationalize will be 6 square roots of 2 over 2. Cosine theta, using our triangle, is going to be the adjacent side of theta, which is going to be square root of 34, over the hypotenuse, which is 6. So cosine theta is going to be square root of 34 divided by 6. That means that secant theta will be the reciprocal of that, and so that would be 6 over the square root of 34, but that is not how we're going to leave our answer. We're going to rationalize it by doing the same trick that we've been doing. So 6 square roots of 34 over 34. And then finally, tangent theta, using our triangle, we know is going to be the opposite over the adjacent, and so that's going to be square root of 2 over the square root of 34, which is actually going to be 1 over the square root of 17. Okay, and so that's going to be square root of 17 over 17. So kind of the reason for that, if you need some more explanation, is that since both of these numbers are underneath a radical, we can actually divide them so that 2 divided by 34 is 1 over 17. And the reason I don't have a square root on this 1 is because the square root of 1 is 1. So I hope that wasn't too confusing. Square root of 17 over 17 is what we would want for tangent theta. And so then cotangent theta, our last one, is going to be the reciprocal of tangent. And I'm going to take the reciprocal of let's see here, this one right here, 1 over the square root of 17, and so that's just going to be square root of 17 over 1, or the square root of 17. Okay, example 6 is very similar to example 5, and so we're going to do this basically the exact same way. First of all, by drawing a picture of a right triangle here, and I'm going to put an angle theta here. And it says that the tangent of theta is going to be 1 over 10. So remember that tangent is opposite over adjacent. So I want my opposite side of theta to be 1. So that would be here. This would be 1. And I want my adjacent side to be 10. That means I need to find the hypotenuse. So again, using Pythagorean Theorem, we're going to have leg squared plus leg squared is equal to the hypotenuse squared, which I'll just call C for a second. If I go ahead and calculate this, that's going to be 101 is equal to C squared, and so C is going to equal to the square root of 101. So I can go ahead and put that on my triangle here, the square root of 101. Okay, so starting with sine theta, and it doesn't really matter what I start with, but I've got to get all of the rest of the 5 of them at some point, so I'll just start with sine. Sine is going to be the opposite side, 1, over the hypotenuse, square root of 101. And so 1 over the square root of 101 is going to equal to square root of 101 divided by 101. That means that cosecant theta, that one's the next easiest to do since it's just the reciprocal, is going to be the square root of 101. Okay, so now I can do cosine theta. So cosine theta is going to equal the adjacent over the hypotenuse. So the adjacent side to my angle theta here is going to be 10 over the hypotenuse, square root of 101. So this is going to be 10 over the square root of 101. And if again I rationalize, that's going to be 10 square roots of 101 divided by 101. Okay, that means that secant theta will just be the reciprocal. And so that will be square root of 101 divided by 10, since I'm just going to take the reciprocal of this one, since that's the easiest thing to go about doing there. Okay, tangent theta was already given to us in the problem, so the only thing left to do is cotangent theta, and cotangent theta is the reciprocal of tangent, so the reciprocal of 1 over 10 is going to be 10 over 1, or just 10. Okay, the last three identities that I'm going to introduce in this section are called the Pythagorean identities, and these are the following. So the first one is sine squared theta plus cosine squared theta, and it doesn't matter what theta is, that is always going to equal to 1. Now this identity can be rearranged however you want to. So for example, what I could do in that identity is I could subtract over cosine squared to the other side, and so that would give me something like sine squared theta is equal to 1 minus cosine squared theta. Or one other thing I could do is I could subtract over the sine squared, and I could get that cosine squared theta is equal to 1 minus sine squared theta. So you need to be aware that there are multiple different ways to represent these Pythagorean identities. The second one involves cotangent and cosecant, so it says that 1 plus cotangent squared theta is going to equal to cosecant squared theta. And again, you can manipulate that however you want as long as you do it correctly using right algebra. And then the last one involves tangent and secant. So tangent squared theta plus 1 is going to equal to secant squared theta. Okay, in example 7, we're going to use the fundamental identities that we've learned so far to find the exact value of some basic expressions. So letter A, we have sine squared of 10 degrees plus cosine squared of 10 degrees. And so what I notice is that is an identity from the Pythagorean list that says sine squared theta plus cosine squared theta, and that is going to equal to 1. And so in this case, since the 10s are the same angle, and we're doing sine squared of 10 plus cosine squared of 10, this answer is just going to equal to 1 by a basic trig identity. In letter B, we're doing sine of 42 degrees times cosecant of 42 degrees. And so what I remember is that cosecant of theta is going to equal to 1 over the sine of theta. And so this is going to become sine of 42 degrees multiplied by 1 over sine of 42 degrees. And since that thing is now the same, it's going to cancel out, and our answer is just going to be 1. In letter C, we've got tangent 46 degrees minus sine 46 over cosine 46. And so the identity that I need to remember here is that tangent theta is equal to sine theta over cosine theta. And so that means I can transform this part of the expression into tangent of 46. So tangent of 46 degrees minus tangent of 46 degrees. And since those two things are the same and I'm subtracting, then the answer is just going to be 0. For letter D, we see cotangent squared 45 minus cosecant squared 45. And so the relevant trig identity that we need to use here is the fact that 1 plus cotangent squared theta is equal to cosecant squared theta. Now this letter D is not quite in that format. It's in cotangent squared minus cosecant squared. So I need to rearrange this identity so that it matches the problem. So I'm going to go ahead and subtract over cosecant squared. So that's going to be 1 plus cotangent squared theta minus cosecant squared theta is equal to 0. And then what I notice is that this part right here, I'll underline it in red, that is the part of the problem that we have in letter D. And so to isolate that part, I'm going to subtract 1 on both sides and get that cotangent squared theta minus cosecant squared theta is equal to -1. And so what I notice now is that this example in part D matches this rearranged version of that Pythagorean identity, and so this is going to equal to -1. Okay, example 8 wants us to simplify the expression square root of 100 minus x squared, given that x is equal to 10 sine of theta. So what I'm going to go ahead and do is substitute in 10 sine of theta squared. And so if I go ahead and square that out, that's going to be square root of 100 minus 100 sine squared of theta. Okay, well, what I notice that I can do now is I can factor out a 100. So I'm going to go ahead and do that underneath the radical. So 100, and that's going to leave me with 1 minus sine squared of theta. Now, this might not immediately jump out to you at this moment, but hopefully as we go forward with these trig identities, you'll start to recognize some things pretty quickly. But this parentheses is now a nice identity. So remember, we know that sine squared theta plus cosine squared theta is equal to 1. That means that 1 minus sine squared theta is equal to cosine squared of theta if I just subtract over the sine part of this. So if this comes over here and becomes minus, that's how I get the identity that I just wrote down. So 1 minus sine squared, which is down here, can be replaced with cosine squared. So this is now going to become the square root of 100 cosine squared of theta. And now I can just take the square root of that, which is going to be square root of 100, which is 10, and the square root of cosine squared theta, which is just going to be cosine of theta. Okay, I'm going to do the same thing in example 9. So I'm going to go ahead and substitute in 7 tangent of theta in for x. And so this will become the square root of 49 plus 7 tangent of theta squared. And if I go ahead and square out 7 tangent theta, that's going to be 49 plus 49 tangent of theta. And just like the last problem, I notice I can factor out a 49, and so I'm going to go ahead and do that. That will leave me with 1 plus tangent squared of theta. I forgot the squared back up here on my tangent, so let me make sure that I write that in. 1 plus tangent squared of theta. Well, we have an identity for this. Remember from our Pythagorean identities, tangent squared theta plus 1 is equal to secant squared theta. And this is pretty much 1 plus tangent squared theta. That's the same thing as this. It's just, reverse. And so it doesn't really matter. It's still going to end up being secant squared of theta. So this is going to be square root of 49 secant squared of theta. And then taking the square root of that, square root of 49 is 7, and the square root of secant squared theta will just be secant theta. Okay, this next example wants me to find cosine theta by using the quotient identities, and it has given me tangent theta and sine theta. So I'm going to start off by writing down the quotient identity that involves tangent theta. So that's tangent theta is equal to sine theta over cosine theta. Well, I'm given tangent theta, so I'm going to plug that in, 2 over 7. I'm also given sine theta, so that's going to be -2 over the square root of 53 divided by cosine of theta. Okay, I am now going to multiply both sides of this by cosine theta, so 2 over 7 cosine theta. Essentially, I'm just trying to solve the equation now for cosine theta. This is going to equal to -2 over the square root of 53. And then to get rid of the 2 over 7, I'm going to multiply both sides by the reciprocal of that, which is going to be 7 over 2. And so this is going to end up being cosine theta is equal to, the 2's are going to cancel out, and so that's going to leave me with -7 over the square root of 53. And since the answer kind of started in that form, I guess it's okay to leave it in that form, or you could go ahead and rationalize it, which would say -7 square root of 53 divided by 53. Either one would probably be okay, again, since the question started with a radical in the denominator. Okay, the next problem wants me to use basic identities to simplify the expression. So what I'm going to start off by doing is distributing this parentheses. I'm going to leave the 7 out front for now and just distribute here. So I'm going to start with doing cosecant theta times cosecant theta. That's going to give me cosecant theta squared. And I'm going to leave the 7 out in the front. And then cosecant theta times negative cotangent theta is going to be negative cosecant theta times cotangent theta. Cotangent theta times cosecant theta is going to be plus cosecant theta cotangent theta. So what I notice is that these two middle terms are going to cancel out, and then there's going to be one more term, which is going to be minus cotangent squared of theta. Okay, so rewriting this is going to be 7 cosecant squared theta minus cotangent squared theta. And I remember that there is this trig identity that involves cosecant squared and cotangent squared. And namely, what it says is 1 plus cotangent squared theta is equal to cosecant squared of theta. And so if I can rearrange that to make it look like what I have in the parentheses here, then I'll be able to simplify that even further. So cosecant squared minus cotangent, that means I'm just going to subtract over cotangent squared theta to the other side. And so that's going to end up being 1 is equal to cosecant squared theta minus cotangent squared of theta. And so that means this parentheses, this part right here, is going to equal to 1. And so what I'm going to end up having here is 7 times 1, which of course ends up being 7 as my final answer. Okay, in the final example, it says to use basic identities, but we're not actually going to use any identities. What we're going to do is we're going to factor the numerator almost like it was a quadratic. So what I notice here is that if I let x be cotangent theta, then this really says here x squared minus 2 times x minus 3. And that's a quadratic that is able to be factored. And so I'm going to factor this numerator like it was a quadratic function in terms of x. Okay, so if I was going to do this, I would need factors that multiply to negative 3 and will add to negative 2. And so that would obviously be negative 3 and positive 1. So this is going to be cotangent theta and then minus 3 multiplied by cotangent theta and then plus 1. So it's almost like it's a quadratic, but instead of writing x, I'm writing cotangent of theta. So I'm going to just transfer that over here. Cotangent theta minus 3 and then cotangent theta plus 1. And that's going to be divided by cotangent theta plus 1. And so what I notice now is that this denominator cancels with this cotangent theta plus 1 in the numerator. And so I am left with my final answer, which is cotangent theta minus 3. Okay, you guys feel free to let me know if you have any questions, and I would be more than happy to answer those for you.